Hey everyone, welcome to The Explainer. I am absolutely thrilled to have you here today. We are going to unpack a really fascinating topic, and my main goal is to completely demystify how true, radical innovation actually happens in the real world. We're going to see exactly why pushing the boundaries means you have to tear down legacy constraints. So, the key insight we're exploring today is this. If you want to win the future, you literally cannot just optimize the past. You have to completely rewrite the rules of industrial physics.
So, think about your own field for a second. What happens when you just completely ignore all those unwritten rules of your industry, and instead you let raw physics and pure logic dictate your strategy? It's a pretty provocative thought, right? I mean, we are all so used to benchmarking against competitors, just trying to make these slight incremental improvements. But what if the very foundation we're building on is completely flawed to begin with?
To radically innovate, we must stop optimizing the past and start from the physical truth. This is really the core theme of our whole journey today. There is a massive, massive difference between sluggish incrementalism, where you're just, trying to build a slightly better version of what already exists, and the hyperspeed of fundamental physics. That's where you start with a totally blank sheet of paper and just ask, okay, what is actually physically possible?
All right, here is our roadmap for today. 1. The first principles mindset. 2. Redefining the vehicle structure. 3. The velocity of vertical integration. 4. Factory as the product. And 5. The repairability paradox.
Okay, let's jump right into Section 1, the first principles mindset.
We are going to take this concept from a theoretical buzzword, the kind of thing you might hear thrown around in a corporate boardroom, and turn it into a tangible, razor-sharp tool that you can use to dissect literally any problem. So what is it exactly? Well, first principles thinking is a rigorous problem-solving methodology that decomposes complex challenges into their most fundamental physical and logical truths, rebuilding solutions from scratch. It is the ultimate refusal to just accept the rules of the game established by the people who came before you. It's not about reasoning by analogy or asking, hey, how did the last guy do it? It's about asking, what is fundamentally true, and how do we build straight up from there?
Moving on to Section 2, redefining the vehicle structure.
To really ground this concept, let's look at a very visceral, physical example that brilliantly illustrates the failure of legacy adaptation. For years, traditional automakers were trying to adapt their old internal combustion engine frames by literally shoehorning these massive, heavy batteries into them, basically just to preserve their brand identity. But when you apply first principles, you get a native, purpose-built EV architecture. You go from high physical complexity with thousands of disparate parts to a design that's meant entirely for high-speed robotics. You shift from slow, vendor-locked iteration to rapid, in-house evolution.
And this leads us directly to the physical mechanics of this breakthrough, which is just incredible. Instead of welding hundreds of tiny metal parts together, first principles engineering uses gigacasting to just print entire sections of the chassis as a single massive piece. Boom, done. Then there's the cell-to-chassis concept. Instead of the batteries just sitting there being dead weight, they actually become load-bearing structural elements of the car itself. Add in a centralized architecture that replaces dozens of fragmented control units with just one local network, and you have radical parts reduction. This creates immense manufacturing density and literally turns the vehicle into a living, software-defined product.
Which brings us to Section 3, the velocity of vertical integration.
Now, once you've redefined the physical product, you have to redefine how you actually control its creation. Because when you think about it, your supply chain is actually a matter of physics, not just a financial spreadsheet. When you rely on external vendors, you are basically accepting physical bottlenecks on your own evolution. You are stuck waiting months in negotiations just to make a really basic design change. But with vertical integration, you have total stack control. This means you can iterate and completely change a design in a single one-week cycle directly on the assembly line. It's the hyperspeed of in-house iteration, totally obliterating the sluggishness of traditional supply chains.
And because you have that total control, you can implement software as architecture. A centralized local network enables over-the-air updates. Think about what this actually means in the real world. Traditionally, a car depreciates the second you drive it off the dealer lot, right? But by treating the hardware merely as a vessel for the software, you completely break that legacy cycle. You create a living product that actually gets safer and more efficient over time, literally years after it was purchased.
All right, Section 4, Factory as the product.
We are going to use the Nevada Gigafactory as our case study here, because to pull off everything we've just discussed, the factory itself actually demands more engineering skill than the car.
Consider the incredibly mundane reality of factory plumbing. The Nevada Gigafactory is massive. We're talking 6 million square feet. If they had used traditional gravity plumbing, they would have had to dig trenches 30 feet deep just to maintain the proper slope. This is what we call the 30-foot trench limit. It's a brilliant Trojan horse concept because it uses basic, everyday plumbing to show how systemic, traditional limits threaten to completely halt an ambitious construction schedule.
So what is truly fascinating here is how they defied gravity. Instead of just accepting the conventional wisdom of trenching the floor, they asked a first principles question. How do we move waste without being beholden to gravity? The answer was the Acorn Vac system. It's a closed piping network that uses a vacuum to pull drainage up into the overhead ceiling space. They completely bypass the need for crippling floor cuts.
And this brilliantly illustrates the business impact. Because the pipes were overhead, the design engineers were no longer constrained by fixed underground trenches. They could optimize the layout density and rearrange bathrooms and workstations on the fly, literally while the factory was being built. The infrastructure adapted to the product, not the other way around. It's a total game changer.
Let's drop the so what anchor right here. Get this, $100,000. That is the exact amount of money they saved in temporary chemical toilet servicing, yes, we're talking porta potties, simply because they could deploy a temporary vacuum center. This kind of out-of-the-box thinking allowed them to hit their aggressive occupancy deadline months before a permanent gravity system could have ever been finished.
So the crucial point here is resource de-risking. By using this vacuum system, they reduced potable water consumption for toilets by up to 68%. This massive reduction completely bypassed municipal utility bottlenecks that so often stall huge industrial projects. They didn't just solve a plumbing issue, you guys. They engineered away a massive operational risk.
Let's look at Section 5, the repairability paradox.
Now, as much as I absolutely love talking about these massive efficiency gains, we have to be completely objective here and acknowledge that radical optimization always comes with hidden costs. On one side, you have the manufacturer's edge, unrivaled energy efficiency, software dominance, and radically slashed production costs, thanks to things like gigacasting. But on the flip side, you have the user's trade-off. Those single-piece monoblock structural parts mean that post-accident repairs are far more complex than fixing traditional modular frames. First principles manufacturing basically shifts the economic risk away from the production phase and directly into the claims management and insurance phase. It is a really fascinating systemic trade-off.
Which brings us to our core takeaway for this explainer. When a problem seems impossible, it is usually because we are accepting the rules of a game established by the past. True power, true innovation comes from defining the physics of your own production. It comes from stripping away all those comfortable industry habits and asking what is actually physically possible.
So I want to leave you with this final thought to apply to your own life and your own work. Are you going to keep optimizing the old legacy rules, or are you ready to use first principles to invent a completely new game? Thank you so much for joining me for this explainer. I really hope this provided you with some truly useful insights into how the world's most innovative minds break down constraints. Keep asking why, keep challenging the rules, and I'll see you next time.